Hi, we are Robotics for Space Exploration.
We are a space robotics design team from the University of Toronto made up of 60 students from engineering, computer science, and life science backgrounds.
This year, the mechanical team has focused on reliability of all mechanical systems. We've addressed key issues in previous designs while keeping designs that work well. This year's chassis is an aluminum extrusion frame with acrylic panels. This keeps weight low while providing stiffness and easy mounting for all other teams. In previous years, we've used a rocker bogie suspension, which has provided structural challenges in the hinges and the differential. We've addressed this by switching to a buggy-style wishbone suspension. This year's mechanical system provides a stable and reliable base for all other teams to mount to. We're experimenting with carbon fiber components for heavy parts, such as the suspension, and we're excited to continue improving.
Our electrical system is powered by 4 LiPo batteries that are 4S and 25C. This provides 14.8 volts to our contactor, which is 400 amps, and gets deactivated and activated by a physical e-stop in series with a remote e-stop that can do this wirelessly. The battery power is input into the power distribution panel, which allocates power for 16 channels with 40 amp and 20 amp auto-resettable fuses. One of the important devices is the voltage regulator PCB, which steps up and down the supply to provide 12, 24, and 48 volt rails for other electronic components. Our PDP also drives power to 4 Falcon 500 motors with embedded controllers. Lastly, we have designed a peripheral PCB which will control the lights on the rover based on its current operation mode.
The rover's manipulator is a 6 degree of freedom robotic arm with a multi-choice end effector and a differential wrist. The first 3 joints are driven by strain wave gearboxes as they have very little backlash and will provide the most similar end effector pose to the desired pose. The last 3 joints of the arm form a spherical wrist, a roll joint followed by a bevel gear differential. This configuration is desirable as it is more dexterous and less cumbersome to reach a desired end effector pose. The end effector is a 3-finger multi-choice design which can switch between parallel and concentric grip direction during operation without physical human interference. The end effector is actuated with a lead screw and motor, and the configuration is changed using a servo attached near the base of the end effector. The fingers have a form-fitting design to adapt to the contour of almost any object. These flexures are 3D printed from TPU for its high elasticity and high durometer rating, as this enables them to grip objects firmly without damaging them. The arm you see here is the practice arm. Its joints and major geometry will be identical to the final arm. It only differs in that it is 3D printed, whereas the final arm will use aluminum sheet metal. This is done for rapid prototyping purposes. This is version 5 of the practice arm, and fully capable of completing all competition tasks. The base station, it will control the arm with either manual or analytical inverse kinematics. The option to toggle between the two is implemented for tasks requiring fine precision or arm positions difficult to attain with inverse kinematics, such as reaching around an object.
Our software stack uses the ROS navigation skeleton and consists of several layers of abstraction, from sensor data to a representation of the environment that informs intelligent traversal for autonomy. We focus on locally optimal traversal using the timed elastic band local planar based on a cost map generated from our Ooster LiDAR data. The metrics for this cost map are elevation and a traversability score of the terrain at each cell in our occupancy grid. The system executes the commands using a differential drive model with move base. We stream video from our camera to our custom GUI, where we visualize current article take locations, manual control inputs from the PS4 controller, and the current state of the rover and task. To improve localization, we implement an extended Kalman filter based on the IMU information and LiDAR-based odometry. We have built a custom state machine-like architecture for tackling the URC autonomy task, and track the state of the rover as it performs the task using a custom state message. This holds the position, goal, and status information of the rover. We approach the task in stages. First, traversing to the GPS goal, assuming a straight line traversal, and using the timed elastic band planner to find good paths to the terrain as we go. Second, we plan towards the ARCO tag when it is visible to the rover, nearing it if it is a post, and passing between the posts if it is a gate. Third, if no ARCO tag is immediately visible, we perform a grid search within the GPS region to locate it. Finally, once the conditions for the post or gate are met, we continue to the next GPS goal until all goals have been met. We use simulation extensively to develop our software stack, capturing the rover's mechanical configuration, integrating sensor information, and simulating terrain to improve our ability to iterate quickly in our autonomy design.
The science payload this year incorporates a sample collection mechanism, a sample analysis module, and a computer vision-based science analysis module. The sample collection mechanism consists of a linear actuator system with 3 independent science analysis modules, each of which is equipped with a bucket wheel excavator and a sample collection repository. We chose 3 to ensure there is no cross-contamination between each of the soil sample sites. After being collected, the soil samples are deposited into the sample analysis module to be further analyzed. It is an optically isolated wet lab to enable our experiments to run unimpeded. In the sample analysis module, which I've opened up, the internals here, the soil samples are tested for the presence of molecules indicative of signs of life. We measure the pH, nitrogen, phosphorus, and potassium content. These tests are performed with preloaded test tubes with chemicals that change colors depending on the pH level, relative concentration, and the relative concentration of the various chemicals. We also test for starch content, such as sugars using the Lugol's iodine test, and we test for the presence of amino acids using the 9-hydrogen amino acid test. Finally, we also test for the presence of FAD, a molecule necessary for the generation of ATP in cells, using the FAD fluorescence test with a PMT. In addition to our work with the physical samples, the science module is also implementing a cutting-edge computer vision algorithm to enable the estimation of grain size distributions of soil samples, and also an NDVI lens to detect chlorophyll in the surrounding environment.
I think you need like at least a pound of force on there.